Hi. Okay, maybe it's working. Yeah, okay. Okay, it's working. So today we are going to start semiconductor in COMSOL. So welcome to my channel. If you are new, then welcome. So okay, so what I'm going to do today? So I'm going to start basic semiconductor simulation in COMSOL. So today I'll start with diode simulation. Okay, so let's start. So at first we'll go with model wizard, and then mm, we can take 2D or 3D or 1D as your wish. Okay, maybe we can start from 1D, then 2D, then 3D, or we can start from maybe we can start from 1D. Okay, then gradually we'll go to 3D. Okay, so at first we select 2D, then we have to select semiconductor from this interface. So we are going to select semiconductor, double click here or just click here, add. So it will add the physics interface. Then have to go to study. So what study we are going to do today? So at first we will do semiconductor equilibrium. So it's the basic thing of semiconductor, not advanced things. After that, we'll do a station. Okay. So at first, you can do the semiconductor equilibrium. So double click here, or you can. So if you double click, then it will go to this interface. Okay, that's all. So here we are going to do 2D. Oh, sorry, on this simulation. Okay, that's not that much fancy. Okay, so at first in the geometry, I'm going to select micrometer. So because we are going to simulate uh, diode, right? So it's diode is micrometer. Then uh, interval. So from so you have to select interval. So from 0 to maybe 0.5, and then 0.5 to 0.5. Then 0.5 to 1. Okay, so that's all. So from 0 to 1 we got uh, semiconductor. Okay, sorry, diode actually. So maybe we can define this part as p type and this part as n type. So then we have to select. This is all about geometry on the for diode. Okay, so you can make it complex. We'll do it in another video maybe. So in the material part, we have to select the material. So you can select. Okay, can I just take it here? So from material, because material, you have to select material from materials. So you can select blank material or add material. So I'm going to select add material. You can do this thing by right clicking here. Okay, right click. Okay, right click, then add material from library. So okay, add material from library. So by clicking here, we'll have to go to semiconductor because we are working on semiconductor. So if you want, you can select silicon, germanium, or any other um, semiconductor, gallium nitride or silicon carbide. as well as so. Today, we will work on silicon semiconductor. Okay, so double click here, it will add automatically. So, okay, that is silicon. So you can just cross it. Okay, so it automatically select the two part of silicon. That's silicon. Okay, so that's all. So then now material is good. We select a silicon diode. Just okay. In the semiconductor part, I prefer to do grouping. Okay, group by space dimension. So it will group you separate the group by domain and boundary. So the whole body is domain and this is the boundary. Okay, the point is surrounding for the case of boundary. Okay, so it's make your work easy actually. Okay, so in the domain, um, so it's totally semiconductor now, right? So you have to define which part is P type or which part is N type. So for that case, uh, so how we can define N type or P type? So we have to dope, right? So by doping, we can make a silicon semiconductor N type or P type. Okay. So how we can do doping here in COMSOL? So in the domain you have to right click and you can see that there is an option doping. So you can select analytical doping model or geometrical doping model. So today we don't want to just explain lots. We just want to work on analytical doping model. So analytical doping, geometrical doping model is kind of straightforward, but analytical doping model you can do it complex thing here. So just we want to do analytical doping model. So click here. So analytical doping model. So for the first part, we select the first part. So then you don't have to say any other thing. So you can see that how his equation is going to solve. So and okay, so we have to work here. So by default, it's selected as acceptor doping density p type. Okay, so by default it's selected as p type. You can make it n type or you can just take it p type as well. So I'm going to just increase the doping concentration. Okay, so I just make it one 10 to the power 17 actually centimeter cube. So per centimeter cube, its doping concentration is 1 10 to the power 17. Okay, so this part we make it as p type. So we are going to make it as n type. Okay, so you can duplicate it just by here, duplicate it and deselect it this way, and you can select it. Sorry, select it by clicking here. Okay, then you have to make it n type, right? So now it's n type. So you can make it as well as 10 to the power 17 or okay, maybe you can take it 2 into 10 to the power 17. Okay, or you can take it on as well. So then it will be unique doping for the N type and P type. Okay, that's all for now. Okay, so what I'm going to do now, I'm going to run the simulation, maybe everything okay. Okay, for in the case of mesh, you can select semiconductor mesh, physics control mesh. So it will automatically mesh it, or you can do it user defined mesh. In that case, you have to define all the things. So yeah, you can make it customize maximum event size. You can define by yourself as you wish. Okay, so then um, you can make it. So for this contract is very crucial, right? So that you have to make a good mesh. So the select is by default fine. So you can make it extra fine. So okay. So as you can see, the mesh is now is very good mesh. Okay. So okay. Okay. If you want to, okay. I don't know. It's going on. Oh no, it's not. Okay. Okay. It's good mesh actually. Okay. So, okay, that's all. So, machine passes, and then you don't have to do mass thing here. So, just you have to run the simulation. Then we'll see what will happen. So, by this time, I want to talk about this thing. So, what we are going to do, actually, we want to see this graph actually. So, this is the carrier concentration graph. Because we as you can okay, you don't need to look at this. Okay, so uh, we'll discuss it after that. So what we have done, what we have done here. So we define the carrier density for p type. We define the carrier density of n type. So we want to see that actually our carrier density is working well or not. So then this is the carrier concentration actually. So by default, COMSOL provide you this actually for 1D. Okay, by default it will provide you. So electric potential as well as you will see that the electric potential from minus 5.05 to 4.15. So you can calculate it. Okay, you can calculate it. Hmm, what's the difference then? The difference is um, okay. So okay. So what's the difference then? The difference is maybe 1.1, right? Okay. Then electric potential is zero point 0.1 actually. Okay. Top concentration. Okay. Don't worry about it. So that's okay. That's the thing. So maybe for your case, maybe it's not look like this because for your case, maybe it's not logarithm scale. So with COMSOL here automatically select the logarithm scale. So if we deselect it, then you can see this kind of figure. So it's not quite good, right? Because the number here is very large. So you have to select the logarithm scale, okay? Then it will look good. Okay. So for on the case, we seen this curve, okay? So it's the basic thing of semiconductor physics, okay? Uh, only you seen this curve in our textbook, right? So if we talk about energy level. So this is the arc length actually. Okay, so we can talk about this thing for this case as well. So it's the arc length. Arc length means the length of the device actually. It start from zero and end in one. So uh, here you can see the arc length start from zero to one. So this is the arc length. So as you can see that this is the whole density, right? So in our model, what we have done, we have defined it as p type. So here the whole concentration will be very high, and for this case, whole concentration will be very less, and electron concentration will be very high. So as you can see that, yeah, in the case of 0 to 0.5, the whole concentration is very high. From zero point 0.4 to zero point 0.5, you can see that whole concentration decrease and it's going to it's kind of zero for after that stage, right? So why this kind of thing happens? So as we know that the deflection region of a diode, right? So this uh, uh, portion is for the defletion region, right? So and after for this case, for this portion actually, here the electron concentration is very high, and hole concentration is kind of zero, not zero. As you can see that hole concentration is kind of 7.55 into 10 to the power 1 into 10. It means 75, right? 75.5. So it's not zero, but tends to zero compared to electron. The electron concentration is kind of 2 into 10 to the power 17, right? So that's the thing. Okay, okay. For energy levels, okay. So in the case of energy level, okay, so this is the diode curve, right? So uh, you know that this is the valence band, this is the curve of valence band, and this is the curve of conduction band, okay? Okay, and the Fermi level of so they are overlap here actually. So we can talk about the valence band and conduction band. So in our textbook or any animation video, you may see that um, electron are going from this portion to sorry, valence band to conduction, right? So electron are going from here to here, then here to here. So then it's pass through the device, right? So and whole are passing through this way. So that's maybe we seen in our textbook. So this is the band diagram actually for our semiconductor. Okay. Now we can just make it 2D. So it's now 1D, right? So you know that is 1D. So we can make it 2D. So for that we have to add another component that will be 2D, right? So we can take another 2D component. So in geometry, we have done the 1D portion. So now we are going through the 2D portion, right? So in the geometry for 2D case, we have to make uh, rectangle. Okay. So in the this case, what we have to take? We take the height, right? It's 0 to 1, right? So for that case, okay, we have to define the width and height. So for the case of width, maybe we can take it 0.5, maybe. Oh, sorry. We have to define the geometrical unit, right? So that's micrometer. So then you can take it 0.5 and height 1. So this is our device. So okay, you may ask that this is uh, the okay, okay. So for on this simulation, this portion was P type and this portion was N type, right? So we have to make this kind of thing. So in the 1D for 1D case, you have to make this division in this coordinates, okay? But for the 2D case, and as well as for in 3D, okay? So you have to divide it in layers. So in the layers, you have to divide it from the middle of the device. So we can put it 0.5. So that's the thing. It will work like that. So there is another way. So you can delete it. Maybe you don't need to delete, but I can show you. So you have to take the rectangle. So for the up for the bottom layer, we are taking the white. what was our height? Maybe 0.5, okay. 0.5 and height will be 0.5 and the base is 0, 0, right? So it will start from this. Okay, great. So it's in 0.5. So we need another layer. So you can just duplicate it, and we have to take uh, this value for same, but for this case you have to choose for y 0.5, then it will work like that. So it's the same process. You can divide by layer, or you can create two rectangles. Okay. In the case of material, okay. In the case of material, as we mentioned before, we are taking the material from add material from library. So you have to go to semiconductor, silicon, double click, and okay. Well, then selected by default, it's selected semiconductor, silicon. Okay, and in 3D component, we didn't take any physics. So what you can do, so as we mentioned semiconductor physics here, so you can just copy it, this physics here, and you can just paste the physics in the here in the component 2. This is the paste semiconductor. So if you paste the semiconductor, then the same physics will appear here. Okay, it's 100% same physics in for the case of 2D. Okay, that's the thing. So if you don't want to copy and paste, you can just add the physics from physics and add physics, then something will appear here. Then from semiconductor, you have to take semiconductor, right? Double click here, then it will appear here. So that's the thing. Okay. So uh, uh, unlike doping model, so we have to select it as upper layer. So it's the P type, and for analytical doping model 2, it's the N type. So it's the bottom layer. Oh, another thing, we made it P type, right? So we can write it here, P. We can also write it here as N. Okay. Okay. In the case of boundary, you don't need to do anything here. Okay. Thank you. Okay. In study 1, now we don't want to run component 1. We just want to run component 2. So maybe we can add another study that will help us. Show me. That's an add study. So we want to run semiconductor equilibrium there, right? So we can add a second study 2 for the case of 2D material. Okay. So in the study 2, we'll run only component 2. Why we choose study 2? I will explain it later. So we don't have to do anything here. Okay. So by this time, we are just recreating the same thing from 1D to 2D. Okay, not nothing special. So we'll get this curve again from 2D, similar curve. So by this time, I can explain what we are going to do in our next video. In our next video, we are going to recreate this figure. So it's the current versus voltage graph of diode. So as we know, the threshold voltage of silicon diode is 0.7, and breakdown, if we apply some reverse voltage, then the diode will break down. So we want to see it in our next video. Thank you. So that's the thing. So in the case of, so you can see that, and for energy level, they by default select study 1, but we are running study 2, right? So we don't maybe we are not getting the result from for this case, And for current concentration, it's also select study 1, but we are in study 2. For electric potential, they also select study 1. The dopant concentration is also study 1. For the case of 2D, okay, they by default just shown the 2D graph, okay. This is the electron concentration, this is the hole concentration, this is electric potential. As you can see that shown the graph for by default they provide the graphs for 1D case, and they provide the 2D graph for 2D case. So we want to, okay, this is the electric potential. Okay, so you can see this is the electron concentration, right? This is the electron concentration. So this one is p type and this one is n type. So electron concentration will be higher in the n type portion, right? So you can see that higher portion is this. So this portion is kind of maybe I don't know the name of the colors. So, kind of I don't know lots of the name of lots of colors. So that's the thing. Okay, and this may be kind of white. I don't know the exact name of this color. Okay, and for the case of hole concentration, you can see that the p-type portion is um, showing the higher hole concentration, right? So okay, though they didn't provide the 2D graph, but we can plot the 2D graph for the case of 2D simulation as well as for the 3D simulation. For that thing, you have to select on the plot group. Okay, just by getting this on the plot group, then right click, then you will get line graph. Okay, okay, then it will appear line graph. Then what you have to do, just you have to just click here. Okay, you have to click line graph, then you have to click define cut line. So it will define cut line this way from p type to n type. Okay, so you have to define the expression. So we want electron concentration, so you can just copy the electron concentration from here. Okay, I will show another way. So you can copy this thing from here, so you can see this, the graph is like this. Okay, so if you don't have the equations, then how will you get this equation? So you have to go this way. Okay, then we'll find, oh, we are working on the 2D, right? So then component 2, right? So you have to go to component 2 and semiconductor, then carrier dopant. Okay, then we want electron doping concentration. Then write this this thing, right? So okay, double click here. I don't know. Okay, so right click here. I don't know why it's not coming, but it's not coming. Okay, okay, electron, double click. Okay, okay, thank you. Now this thing is the graph. Okay, so you have to then duplicate the graph. Okay, duplicate. Then you have to plot the graph of what? Hole, right? So then you have to go again, semiconductor, then carrier doping, then hole, then this is hole concentration. So that's the thing. So as we mentioned before, you have to see it in logarithm scale. So click on log scale. Then this is the graph as we seen before for on decay. So for on decay, for 2 decays. That's the same, right? Maybe. Oh, yes, obviously. Why not, right? So, okay, that's all. Okay, okay. So we can make it 3D as well as. So if you want to make it 3D, then you have to click on 3D. So it will appear in 3D. Then geometry, for the case of geometry, you have to select actually block, then select block, then wide will be maybe 0.5, depth will be 0.5, height will be 1. Okay, you have to select micrometer, right? So so that's our model. So as we mentioned before, you can um, hmm, divide from layer, or you can build to block. Okay, so in this case, I'm dividing from the layer. Okay, 0.5. Okay, they automatically done. So sometimes it may seem wrong for your case, because you have to see this thing actually, as well as you have to look there at there. So in your case, maybe it's from my case, it's by default click in bottom. So for your case, maybe it's by default click from right. So if it's click in right, then if you failed, then it will appear a problem. So the problem is from the right. Okay, from the right, what we have to select actually. Um, Weight is 0.5. So from right, you are layering 0.5. So it's not the width is not that much. Okay. So if you take 0.25, then it will okay. Oh, sorry, from right. So it will okay, right? It's making 0.25. So that's the thing. Okay. So you have to select top or bottom. If you take top, it's okay. It's also okay. If you take bottom, it's also okay. Okay, that's the thing. Thank you. For the case of material, as I mentioned before, you have to click on material from library, then semiconductor, silicon, double click, it will appear, automatically select whole model. Then, okay, as well, okay, again, we have to copy the semiconductor, and you have to paste the semiconductor in component 3. So paste semiconductor. Okay. So by default, it's domain. For the case of domain, as in seen before, and for the case of 2D, we have to select unlike topping model for P, topping model for N. Okay, and for the case of boundary, you don't have to do anything. Okay, in the case of mesh, yeah, automatically this select finish control mesh normal. So by default mesh is okay. If you want, you can make user control mesh or anything. So now again, I want to run another study. So add study semiconductor equilibrium. Okay. So we don't want to run component 1, component 2. We want to run the component 3 actually, right? So compute. Okay, close it. Okay. So as I mentioned before, tomorrow's video will actually apply the voltage. Today we didn't apply any voltage in our model, right? So in tomorrow video, we'll apply voltage. Okay, in diode, we'll apply forward voltage as well as backward voltage. Okay, then we'll see the um, diode current curve of current of diode, right? Current versus voltage. So okay, it will take some time. If you didn't subscribe our channel, you can subscribe if you want. If you don't want, then okay, it's okay. Okay, so That's the thing. Okay, it's taking time. Oh, my laptop is little bit slow. Then don't worry. Maybe your laptop is so fast, so your run already completed. So, but my laptop is little bit slow. It's taking so much time. So as you've seen, for we are getting the same result for 1D, for 2D, for 3D, but the time of simulation time for 1D was very fast. For 2D, it's uh, uh, bit time consuming, and for 3D, it's taking lots of time for simulating a single diode actually. So when you will work on complex design, then it will take lots of time. So you need a very good computer or very good laptop to run this kind of thing actually. And I want to mention another thing for your help, that is, please plug in your charger if you are using laptop. So because COMSOL puts lots of pressure in our battery when you just unplug your charger. So then uh, within some days or some months, your laptop's battery will be dead. So to be safe, please please when you are working on console, plug in uh, charger. Okay, so it's taking lots of time actually now. Okay, but don't worry, it will work actually. It will work. Okay. I don't know why it's taking lots of time actually. Okay, what? Okay, it's going to. I don't know. Oh, I got it. I got it. I've seen this problem before. Okay, that's why it was taking lots of time. Okay, so don't worry about it. For the case of 3D simulation, it's not comparatively easy as it was before. Okay, for the case of 3D simulation, you have to select mesh. You have to select user control mesh. Okay, so you can just disable this to size. If you sorry, you can delete it tetrahedral. Okay, for 3D simulation, COMSOL does not work for tetrahedral. Show some problem. So if anyone knows any solution, you can tell me. So I know on solution, that is sweep. If you select sweep as a mesh, then it will work actually. So now I select sweep, and for the case of size, maybe I can select extra. Okay, it's a kind of very bad mesh. Okay, so it's actually diode, that's why it will not affect that much. So it will just reduce the simulation time. So now I can compute. Okay, and maybe it will not take that much time. Okay, as you can see, it's not taking that much time. Okay, it's done. So that is our electron concentration. That is our whole concentration. Okay, you can see it like this way. Electric potential. Okay, have we done anything wrong? Light of model, light of model. Okay. Okay. So silicon. Semiconductor material. Okay, we didn't done anything wrong, right? But I think it's not satisfactory result. Hmm, okay, that's okay. Okay, so if we see the 1D graph, then it will be more clear. Okay, define. Okay, something. What are the difference here? I don't know. What's going on? Cutting. Okay, did I get it? Just okay, and not cut. Study. Study tree. Then line graph. Then it was all good for 3D. Okay. Then define cut line. So it will look like that. Then have to put equation. So as we get the equation before, so we just don't copy it and we just don't paste it here. But one thing you have to take it in mind, it's not semiconductor 2, it's semiconductor 3 actually. Okay. So it's working, but not in continuous. Okay. Sorry. Working, but not continuous. Okay. I got it. Duplicate it. And this is not, and this is actually inside the focus. Okay. Okay. It's also working, but not continuous. So what's the problem is maybe I don't know. I did written down definition or English. Then maybe it will work. I don't know. Just let me check it. So it's taking some time. Okay, as you can see, for the normal mesh, they didn't show good result, but now it's quite good result, right? Okay, let's go. Okay, now it's quite good. Okay, so it's not continuous. Uh, Still, it's not continuous. So what we can do, we have to then do some fine mesh. Or another thing you can do, fine, okay, then what you can do, okay, let's take it now, rename now, domain, is domain, okay. Oh, you don't need to do this, okay, you don't need to do this, okay. So we took some fine mesh, okay, stuff fine mesh, okay. So for 3D, have to be Suji for um, taking mesh actually. Yeah. Otherwise, it will not work uh, perfectly. You got it? Okay. So we select a very fine, very good mesh. That's why it's taking lots of time actually. So don't worry, it will finish. So it will start conversion. Okay. Just be patient. Be patient. Hmm. Mhm. It's okay actually. What's going on? The error is changing. Is master decrease. Okay, it's decreasing actually. Okay, it's perfectly working. So it's all perfectly. So now it's quite good result, right? It's showing quite good result. So if we send like this, then you can see it's resulted quite good. Okay. So now we can see that. So you can see that the result is okay, quite good, but not that much close still because of meshing problem. So you have to choose a more good mesh actually. Then it will work actually. So that's all. We are getting kind of similar results from 2D, from 1D, and as well as from 3D, right? So that's the thing. Yeah. Thank you. Thank you so much for your time. Okay. No, I'm stopping the recording.